my name is Jacob Jennings, and in this video I'll be detailing the development process for my Adaptive DJ interface for the Microsoft Adaptive Prototype platform. This project began with my daily skim of Slashdot, where an article detailed an upcoming student contest at the 23rd ACM Symposium for User Interface Software and Technology. It was held in several really interesting venues in New York City. This contest involved the prototype from Microsoft. It's called the Adaptive Keyboard, which is really best explained by watching the video from Microsoft Applied Sciences. You can find it by searching Adaptive Keyboard on YouTube, or you can also find it by going to acm.org/UIST and clicking on the student contest section. Just over 100 teams requested keyboards. Due to overflow, teams were asked to submit a pitch for their projects. I made a short video on YouTube detailing my project, or at least the idea. In this video, I'll focus on strictly the development process. Check out my other blog for the demo and event coverage. It might give you a better idea of what the project was all about before I dive into the technical details. After a bit of trial and error, I settled on an overall design including Silverlight, C#, and C++. Basically, the user experience is completely Silverlight and C#. I'll get into why I had to include C++ as well. The key and touch area run as separate Silverlight applications. From now on, I'm going to refer to the keyboard. I'm talking about the actual tactile keys, and the touch area as being obviously the touch area above it. So between these Silverlight applications that run each of these sections, communication is possible, which is demonstrated in this project. The use of C++ for the application was required due to the limitations placed on Silverlight applications for security reasons. Specifically, some Windows APIs are unavailable to Silverlight, unfortunately including the MIDI API, which I required for this project. Essentially, my application, which is a DJ controller, runs as a MIDI controller device, which can be mapped to any number of applications which accept MIDI controllers. For my demo, I used an open source DJ project called Mix. I'm going to just skim over the Mix website quickly here to give you an idea of what we're working with. Mix is a really great DJ platform. Most DJs nowadays are really going digital in the sense that they use vinyls that are either time-coded or actual strict controller devices that are USB. But either way, DJs are using software like Mix or Tractor or Virtual DJ. But Mix is really great. It's widely used, community developed. It supports vinyl control from turntables. And best of all, it has a great MIDI scripting engine, which can be used to support a wide range of hardware control devices, which allowed me to use basically just XML and JavaScript to map the controls I was designing on this interface to actual controls in the software. This meant that I didn't have to dive into the Mix source code, which was good. Here we have an overview of Mix's MIDI scripting usage. Essentially, we're using this to map MIDI signals we're generating from our emulated controller device to functions within the DJ software. An XML file is used for each control mapping, and these mappings can refer to functions defined in a JavaScript file to allow for more fine-tuned control. Mix also has a MIDI learning wizard where you can tweak individual controls one at a time so that the software can recognize what MIDI controls are being manipulated to make a kind of a quick and dirty mapping to start with so that I could kind of see how the formatting works and later add controls that weren't included in the wizard. Literally every controllable item in the software can be manipulated using the MIDI scripting interface. Here's a quick illustration I made to sketch designs on, which I submitted to the developer wiki during the month of development that we had. Here's an overview of what you need to build Mix under Windows. Mix is multi-platform, but is used most widely under Linux. The only difference here is that I use Visual Studio 2008. This is the reference to the Windows MIDI API, which I use to send MIDI events. Primarily, I use the MIDI out open and the MIDI out short message function just to send some basic controls for sliders and toggles. I also use this table for a quick reference for MIDI codes. Building MIDI short messages without a library support turned out to be kind of an exercise in bitwise logic. I use the note on, note off, and control change messages. Controls change messages were used for the sliders. After a bit of research about how MIDI works, had kind of a eureka moment when I realized that this design model would actually work. While I could find everything I needed to output to a MIDI device, I couldn't seem to find anything about emulating a MIDI device, that is, use software as a controller, or connect a MIDI output in one software to a MIDI input in another. And it turns out all I needed was a loopback MIDI device, would basically just forwards messages from the output to, or from an input to an output, and it makes itself available as a MIDI input and a MIDI output device on the system. I selected it as my output device in my software, and I selected it as the input device in Mix, and voila, everything works. LoopB is one of many solutions, and it's free for personal use, so this is what I used. As it turned out, I didn't actually need to dive into the source code for Mix, since I ended up using a MIDI interface, but it was nice to have the latest developer branch of Mix, so here we're checking out the development branch of Mix. It's pretty simple. I like the ease of use of Bazaar, and how it integrates into your shell right-click menu in Explorer. So here we're viewing the Silverlight project for the keyboard in Microsoft Expression Blend 3, which I got off of MSDN AA, which is available to all of us engineers. I relied heavily on examples provided in the demo applications with the SDK for Microsoft, and it looks like a mess on screen here, but it makes a little more sense on the keyboard. Note that I use Visual Studio and Blend to edit the Silverlight XAML, which represents the GUI, or the user interface, and the C# driving the interface. As you can see, we have keyboard key objects with multiple key states, representing key states when different modifier keys are pressed, like Control Shift. Now we're viewing the same project in Visual Studio. The GUI we saw in Blend is completely represented by this XAML code. For example, the D key in the normal state shows playbutton.png image. Here's a few icons I designed in Illustrator and Photoshop for keyboard use. Now here's the driving code behind the keyboard XAML. Now the way Silverlight works is that XML code, or XAML, is used to represent how graphical elements are presented to the user, and C# is kind of what drives it in the background. We use a local message sender in system.windows.messaging here for inter-context communication, which means basically my Silverlight application in the touch area to the Silverlight application that runs the keyboard area. We have to tie into the adaptive runtime to get the keystrokes, since the context doesn't actually receive them directly. It works just like a normal USB keyboard in that they go directly to the program in focus. So we have to kind of jump in the loop there to get the keystrokes. We keep track of the shift key status to know which MIDI signal to send here, since some keys have different functions while shift is pressed. This mess of numbers just maps key codes, or the codes that the keyboard actually produces at the hardware level for each mechanical key, to a mapping of MIDI note numbers, which I just made a chart of mapping to functions in the target software Mix. Here are the thumbs I use for the sliders. A thumb is just what you call the part of the slider you grab. I imported these graphics from an Illustrator file. I used the included slider object in Blend and made a modified copy for each color. Making these custom sliders didn't require any coding, just graphic manipulation and using the user interface in Blend, which is pretty nice. Here we can see a representation of what will be shown in the touch area above the tactile keyboard area. Blend is really an amazing tool for graphic user interface design. It allows you to apply transformations and effects to objects almost like you're applying them in a program like Photoshop, which really reduces on development time and producing a good interface, because you don't have to go in and modify specific values. You actually see what you're getting as you're working on it, and you can apply transformations and colors, and it's all pretty cool. Here I'm showing how I did some stretch and rotation on the text elements Deck 1 and Deck 2. As I explained earlier, the custom sliders were created in Blend with an imported thumb graphic. A simple right-click opens the XAML code generated by Blend. The transition from GUI design to the actual driving code behind the software is fairly smooth with Blend and Silverlight. In the event section, you can connect events to functions in the C# code. Simply double-clicking on an empty slot in the events section, representing a graphic element in the interface, creates an empty skeleton function and connects to it, allowing you to quickly move from a graphic design, like this example here, a button, directly to what that button is going to do in the code. Back in Visual Studio, let's take a look at the C# code driving the touchscreen. You can see in the Solution Explorer that the contents XAML and C# code are similarly named and grouped together. Here you can see we are referencing a few Windows API libraries, most notably the messaging, which is what we'll use to communicate between the keyboard and touchscreen contexts. Now the idea here in my design was that the touch context will handle all the message passing to the primary C++ program, where the messages will be interpreted and forwarded as MIDI signals to our final destination mix. Since the touch context is the one communicating with the C++ program, the keyboard context sends its messages to the touch context through the Windows Messaging API. Here we dispose of the messaging object. The program sends the context a message letting it know that the program is shutting down, so we let go of that communication channel so we don't have to open a different named one and leave garbage in the memory. The slider value change functions are called when a slider is moved. First I check if it's moved far enough for it to matter, then I forward the message to the C++ program through the context object. Now these arbitrary numbers you see were selected in the value range for the MIDI control chains messages, and I kept track of which is which in just a chart I had on a piece of paper. So they look like crazy values, but honestly it's just mapping sliders to specific controls I had written down. The button defaults click function sets all the sliders ranges and default middle values whenever the user clicks the defaults button on the touchscreen. This allows you to return to a flat normal setup, I guess you could say, if you've messed with a lot of controls and you want to quickly start from, a normal setup. You can see here in Blend how the button is connected to the function. The range for the sliders, or the value range for the sliders, represents the value resolution supported by the MIDI control change standard.